Okay, so in this session we are going to learn logistic regression, and we are going to learn how to run or build a logistic regression model using R and RStudio. Let's get started. So this is your RStudio software opened in front of you. Let's go to File and New File and R Script. And if you focus on this part, a blank file opens where we are going to type our commands. Why we are building a script is so that by the end of this session you will have a file ready with all of the commands written here, which you can practice later in your own time. So let's read the file first. I'll put comments also so that you follow what we are doing here. So we are going to read the file, we are going to view the file, and we are also going to plot the data in this part. Okay. Let's read the file into data frame using the read.csv function, and our file is labtest.csv. And the next thing we want to do is just view what is there in the file. So I'll put view x. Right. So first of all, let's just run these two lines and see what happens. So if you focus here, we have read the data, and when you do view x, when we run view x, this table will open here in the next tab, and here I can see the contents of the lab test file. As you can see, it has three columns. The first column is an ID. Supposedly it's patient's data, so these are ID number of patients. This is the outcome of the test, and this is the test value. So if you just scroll through the file, in the outcome column, we see that we have two possible values, 0 and 1. So making this a binary response variable. So what we are trying to do is, based upon the test value, we are going to make a prediction by building a logistic regression model whether the patient whose lab test has been done is healthy or sick. If the outcome is 1, the patient is sick. If the outcome is 0, the patient is healthy. Please remember that. So just scroll through the file. We see that we have a total of 41 observations here. We have a total of 3 variables in the file, and these are the different test values. As you can see, some test values are duplicate as well. For example, you see we have patient 1's test value is 44.1, and the test value for patient 3 is also 44.1, and we have a couple other repeating values, like you see for patient number this value here is 42.2, and probably we have another value 42.2 somewhere here. This value is also 42.2, so we have a couple repeating values, but that really doesn't matter. Let's move on and let's plot the data to get an idea of how the data or its distribution looks like. But before we do that, let's don't ever forget to run that str function and look at the structure of the data frame. When I do run str, this is what I get. It's a data frame. There are 41 observations of 3 variables, and these are the variables: ID, outcome, and test value. Remember, outcome is my binary response variable. Test value is my independent variable. Now we can go ahead and plot the data. So I'll say plot. So I want the test value to appear on the x-axis, and I want the outcome to appear on the y-axis. Let's run it. And here we see a plot of the data. Remember, I showed you that there's a couple of repeating values. You see it's 44.1 and 44.1 and 42.2, and there was another 42.2. If you look at the plot, those dots have been plotted over top of each other. So they are not obviously separated from each other. Those two same values are plotted on top of each other. But I'm going to separate them somehow by using a simple trick. Why I'm doing that is we are going to use this later in the video, because we would be counting the number of cases which fall into a certain category. So it's easy to do that. I'll say plot Again, the test value is on the x-axis, but this time I am going to plot the outcome with a jitter using the jitter function. And I am going to add a small jitter of 0.20, and I'll show you the effect just in a moment. Now when I run this command, where outcome is being plotted with a jitter, you will see those 2 points which had the same value will no more plot on top of each other, but they will be slightly separated. Look at that. Let's run it. Look at the plot here now. You see those values of 42.2 and 44.1, which were like identical points. Now you can see them clearly as separate points, 2 separate dots, although in the same place on the x-axis, but there is a small jitter added on the y-axis or the outcome, so that we can look at those points separately. Anyways, that was about the plotting of data. And just taking an idea, we have our test values ranging from, let's say, about 40 to about 40, slightly above 46. On the y-axis, we have our outcome. The outcome is either 0 or 1. That's why we see data plotted only on either this line of 0 or this line of 1. Let's get back here and try to build a baseline model first. Okay, what's a baseline model? Remember, for a baseline model, we don't want to use any variable in building the model, but we just want to see the distribution of data, and we want to predict on the basis of the majority outcome in our dependent variable. Let's run this command of table and let's build a table only on the outcome. So when I run this line, this is the table that I get. It shows me the distribution of my dependent variable, which is the outcome. So in this data, I had a total of 41 observations, out of which those with label 0 are 21 and those with label 1 are 20, which means there are 21 healthy people and there are 20 sick people. So it turns out 21 is a majority. So I'm building a baseline model, I'm going to go with majority, and I will simply say that everyone is healthy based upon the majority vote. So then what is the accuracy of my baseline model? It is 21 divided by 41, which is about 51%. So if I make my decisions based upon the baseline, which is by not using any other variable or by not building any model, I'm deciding purely on the basis of taking a majority vote, and I am predicting that all my people are healthy because the percentage of healthy is more, but my model is only 51% accurate. It's just 51% accurate, which is not really doing very well. So what I need to do is I need to build a logistic regression model, and I have to take that independent variable lab test into account as well, so that I am able to improve my accuracy of making predictions about whether a person is healthy or whether a person is sick. So let's get back here now. And before building the logistic regression model, let's do a very quick review of the odds and logit and probability that we have already studied in class. So I'll put review, and first of all, let's try to understand what did we mean by logit. So remember, logit was y is equal to b0 plus b1 times x. This was our logit. Next, what were the odds? Odds were e raised to power y. Odds were e raised to power y or e raised to power logit. They were the odds. And the third thing, how did we calculate probability? So we had calculated the probability by e raised to power y divided by 1 plus e raised to power y. This was the probability. So remember, this is logit. Logit is simply y is equal to beta naught plus beta 1 x. Odds are e raised to power y, and probability is e raised to power y divided by 1 plus e raised to power y. Why we are doing a quick review of these things is we are just going to get into these concepts, so it's a good idea to keep them in mind at this stage. Let's move on now and build a logistic regression model. Let me call that model. GLM is the function that we use, general linear model. And I am going to predict outcome from test value. My data is in X. And since I'm going to build a logistic regression model, I have to pass this additional parameter, family is equal to binomial, by letting the GLM function know that I want to fit a logistic regression model where my response variable is a binary variable. That's why I have to pass this parameter, family is equal to binomial. I may put binomial within quotes or without quotes, it doesn't matter, it will accept it both ways. And remember, whenever we build a model, we have to call the summary function to look at the model's coefficients which have been calculated. So these two lines are going to build the model and show me the model's coefficients or the summary. Let's run these lines now. So this line builds the model, and finally let's call the summary function, and here we have the summary of the model. Let's focus on this part. The intercept is 56.3369. This is the standard error, z values, p values. It's significant. Looking at the independent variable of test value, the coefficient is minus 1.3053. The probability value is much below 0.5, and this independent variable is also significant. The AIC value of this model is listed here. It's 39.161. Remember, we have talked about AIC in another lecture. And AIC is useful when we have to compare two models. So remember, the model with a lower AIC value is always a better model. So having built the model, let's try to focus on the coefficient of test val and try to understand how to interpret the coefficient, because that has been something that we really need to understand. First of all, the coefficient comes with a negative sign. So remember, what does the negative sign mean? Before we go into that, remember we have two outcomes in our case. Value 0 means the person is not sick, the person is healthy, and the value 1 means that the person is sick. What does the negative coefficient of test val here signify? So remember, the negative sign says that the lower the test value, the more likely it is to be sick. Or to put it in other words, decreasing the test value, the odds of being sick are going to increase. Or the other way around, increasing the test value, the odds of being sick will go down or they will decrease. So this is what it signifies. So let's continue, and let's play with the model parameters a bit. So I'm going to write here our model parameters, and what do we have now? We have B0 equal to 56.3369. We have B1 equal to minus 1.3053. And let me just take a value that I want to check, test value, as 42. So I want to calculate logit for this value 42. So what is logit? Just saw a while back, y is equal to B0 plus B1 times value, that is logit. And let's print y as well. Okay, so let's run these lines and try to calculate the logit value for test value 42. So this is the 1.5143 is the logit value for test value 42. Let me change the test value to 43 and see what happens to the logit. Previous test value was 42. I have changed it to 43, which means I have increased the test value by 1 unit. And I want to see the effect on the logit. I have increased the test value by 1 unit from 42 to 43, and I'm going to recalculate the value of the logit, and I'm going to see what is it going to be this time. First of all, remember the coefficient of test val had a negative sign. I am increasing the test value. This negative sign shows that this logit should now go down. It should decrease. I must get a value of logit less than 1.5143 this time. Let's see if that is true. With 42, my logit value is 1.5143. Let's see what is the logit value with 43. So I'll run this line and the next, and let's print the value of logit, and for sure it comes out to be less than the previous one because of that negative sign there. But interestingly, let's find how much that decrease is. So 1.5143 minus 0.209, and I'm sure you've already guessed the answer. The answer should be the same as this here, the coefficient 1.3053. You see the difference is 1.3053. So here is another way to interpret your coefficient, which is that by increasing the test value by 1 unit will decrease the logit or log odds of falling sick by 1.3053. Let's repeat that and try to understand it again. Increasing the test value by 1 unit will decrease the logit or log odds of falling sick by 1.3053. Similarly, decreasing the test value by 1 unit will increase logit or log odds of falling sick by 1.3053. This is what is meant by this value of the estimate that we had here. Remember, this is not multiple regression or simple regression. That's why we are interpreting it in a slightly different way. This decrease or increase in the independent variable by 1 unit is causing the logit to increase or decrease by this amount, which is the coefficient value. So I hope so far what we have done is clear to you. Let's do a very quick recap of what we have done so far. We have written the data file. It is always a good idea to look at your data first, look at the structure of the data frame, and always make a small plot of data and look at the distribution of values. And that is what we had done in this particular part. Next, since it's a logistic regression problem, we tried building a baseline model first by looking at the distribution of our response variable. So it turned out that our response variable had only 2 values, 0 and 1. 0 was in majority, so we predict majority as healthy for everyone. But then when we calculated the accuracy of our baseline model, it was only 51%, not really good. Next thing that we did was we built a logistic regression model and got the model's coefficients. When we got the model's coefficients, we tried to understand what is meant by this coefficient of the independent variable, how to interpret that value, and we saw how to interpret it in different ways. And then using the model's parameters, this was our model, the regression equation, y is equal to beta naught plus beta 1 times this value. We have the values listed, and we practically saw that by increasing the independent variable by 1 unit, what happens to the logit? The value of the logit changes by exactly the amount of the estimate or the coefficient that we have calculated.